Okay, hello everyone, and first of all, thanks to organizers for this opportunity to be here. It's really nice to be back, and I had a lot of fun on previous meetings, and I'm really looking forward for the rest of the week. So I'll be talking about the formation of galactic disks in the early universe, both in general and specifically about the Milky Way disk. And I hope it will be a nice connection to some of the talks later today and more on disk formation tomorrow morning. It will not be an understatement to say that with the advent of ALMA in JWST, there was a paradigm shift in galaxy formation, because before it was believed that galactic disks form relatively recently at redshifts around 1 or 2. And this was motivated by the view of galaxies at higher redshifts by HST and ground-based IFU instruments, where galaxies were very irregular, very clumpy, nothing like nice thin star-forming disks that we see in the local universe. However, this is the red frame UV, so it's very biased towards actually star-forming environments. And now with JWST and ALMA, we have access to red frame optical and ISM kinematics in cooling lines at this high redshifts, and it became clear very quickly that disks are, in fact, not only common, they prevail out to very high redshifts. So these galaxies can form very early in the universe. And closer to home, now it's also possible to see the imprints of disk formation in our own Milky Way from the kinematic and chemical distribution of nearby stars, as for example shown in this plot from the paper led by grad student at Harvard, Vedant Chandra, where what it shows is the distribution of orbital circularities of nearby stars as a function of their metallicity. So metallicity here can be roughly thought as a proxy for the formation time. And the stars at high metallicities that formed relatively recently are all piled up near this circularity of 1, which corresponds to this configuration in a thin disk, similar to nearby typical star-forming galaxies. But the new thing that was discovered quite recently, and here are a few papers where the discovery was made, is this dynamically kinematically hot component at very low metallicities, which is thought to reflect the early stage of galaxy evolution before any disk was present in the Milky Way. And the same data, we can see this sharp transition between these two regimes, so we can see how our own Milky Way disk spun up. And in the Milky Way, this transition happens surprisingly early. So, for example, based on the results from cosmological simulation like TNG 50, we can see that only roughly 10% of Milky Way-sized disk galaxies at redshift 0 formed disks as early as the Milky Way. And in fact, in TNG, we were able to find the one that resembles Milky Way very closely in this space of orbital circularity and metallicity, and Vedant also was able to go through like different events in the history of this galaxy and map how these different features were formed. And I will not go into details about this, so if you're interested, you can ask later or check out our papers. But what I will be talking about in the rest of this talk is us essentially looking at this early phase of galaxy evolution and trying to understand what's going on here. So how galactic disk forms in this early universe, and what are the effects of detailed star formation and feedback modeling. And to do this, we took this galaxy from TNG 50 that resembles the Milky Way, and we simulated with different folds and a more detailed high resolution and more detailed star formation feedback and ISM physics. So here's the comparison. This is the simulation. So for the new simulation, this new simulation is run with the ART code. So I'll be labeling ART. And here's on top is this new simulation, and the bottom, for reference, this is the same initial condition, same galaxy, but in the original TNG model. So quickly, the key differences between these two simulations, apart from different folds, is that the resolution is somewhat higher, but more importantly, they're way more broad range of physical processes modeled in this new simulation, including explicit cooling down to very low temperatures, which is dependent on metallicity and incident radiation field that is modeled on the fly, and explicit model for small-scale turbulence, star formation that's coupled with this turbulence on small scales, and more detailed model for star formation and feedback. So after we put it all in there, we can see that there are qualitative differences in the evolution. Even though on large scales we can trace like the same filaments and the same global structures, but on small scales we can see much more dense cold material forming in this new simulations, and this is which is completely missing in the original TNG model, which is because in TNG at these high densities the thermodynamics of gas is replaced by effective equation of state, which corresponds to much higher temperatures, much higher pressures, which prevent formation of this dense structures. And this abundance of dense cold gas makes qualitative differences in the star formation history of the galaxy. So here's the total stellar mass and the star formation rate in this galaxies up to redshift around 3. And you see that with this new model, star formation becomes much more efficient early on and significantly more bursty. So at early times, the star formation rates can be order of magnitude even more higher than in TNG model, but even though later times they catch up to each other. And importantly, also the variations of the star formation rate are significantly larger. And also in this new model, we can see these two qualitatively different regimes. So first, the star formation rate very quickly ramps up, and then it reaches a peak, and then it steadily declines. And this transition point at around redshift 7, it in fact corresponds to the formation of a thin disk at this very early time. So here again, this shows the orbital circularities of young stars, and at the moment when they're born, and at this moment, most of the stars start forming in a thin disk configuration. And here, I would remind you that this initial conditions is not a typical Milky Way mass galaxy from TNG simulation. It's a galaxy that formed disk relatively early. And in TNG, this time corresponds to redshift around 3 for this galaxy, while with this more detailed ISM formation feedback physics, the disk formation shifts to much earlier time. In this case, it happens at around redshift 7. And at this time, the properties of this disk are consistent with the low metallicity population of the Milky Way stars, which I'll not show, but if you want, I'll be happy to chat about this. But overall, all this early, very efficient, bursty star formation and early formation of disks is very reminiscent of this new result seen by ALMA in JWST and high-redshift universe. And in fact, if we compare this new simulation, which is here shown with blue line, it resembles these early galaxies both in terms of early disk galaxies, both in terms of rotational support of the gaseous disk and for some of the galaxies location on the main sequence of the relation between the star formation rate and the stellar mass. It means that some of these early disks seen by ALMA and JWST can be progenitors of Milky Way-like systems at redshift 0, but it's only some of them because many there are also galaxies that are way too massive and star forming, so they will be progenitors of more massive early type elliptical galaxies instead of these clusters. Another interesting result is that as the galaxy in the simulation evolves, this early burstiness, due to this early burstiness, it explores the entire range of star formation rates observed with JWST at this early time. So it means that the scatter, the observed scatter can be explained by burstiness. So now, having the simulations, we can go and see how the ISM and star forming properties on local scales of star forming regions is different from typical star forming galaxies at redshift 0. And this is thanks to one of the key features of the simulation that here, instead of assuming local star formation efficiencies per free fall time, as often done in simulations, we can forward model it based on the local properties of turbulence, which is also forward model in the simulation. So we can predict the spatial and temporal variations of the star formation efficiency per freefall time on scales of star forming region in each cell, shown in this map. So in this model, the star formation efficiency, the model that we use, the star formation efficiency is the exponential function of the local viral parameter of turbulence on small scale. So in principle, predicted star formation efficiency can be any values from 1 to 0. But interestingly, when we look at the actual values realized in the simulation, they are quite close to what is observed in the local universe, close to 1%, even below that. So this is lower panel shows the average value of star formation efficiency per freefall time in star forming gas, and the values are lower than 1% due to a high level of turbulence. So turbulence provides singular support, so it pushes the values of efficient freefall time to below percent. And another interesting feature is this significant variations of the star formation efficiency per freefall time. And again, this is the average over all star forming gas in the galaxy, and early on it can vary by more than order of magnitude and then by a factor of a few. And in fact, this variation of the star formation efficiency contributes significantly to the burstness of the star formation rate in this galaxy. So this is another channel how star formation can be bursty, which is often omitted in cosmological simulation. And finally, another result that I want to highlight is the connection between star forming gas and molecular gas, because in these simulations we also have a non-equilibrium network for molecular gas, formation and destruction of molecular gas models independently of the star formation, and therefore we can look at the correspondence between the two. And after the disk forms, here at the bottom, this panel shows the gas mass. So after disk forms, molecular and star forming gas roughly follow each other, but at earlier times they decouple. So the star formation proceeds in the gas before it's able to be converted into before it's converted into molecular gas, or so essentially star forming and molecular gas are decoupled, as was previously argued also in the literature. And in the last couple of minutes, related to this, I'd like to highlight the work by another graduate student at the University of Chicago, Eva Paulsen, who looked into this in much more detail in more idealized setup of isolated dwarf galaxy with the same star formation feedback and ISM physics, but with varying the metallicity of the ISM in controlled fashion. So, and as we reduce the metallicity of the ISM down to very low values, 1% solar, you can see that the ISM becomes progressively more smooth, so the formation time of cold gas and molecular gas become longer, and the molecular gas becomes quickly dispersed by stellar feedback on time scale shorter than it can form, and as a result, the abundances of molecular gas in this low metallicity environment become very low. And none of the existing analytical models can actually capture this behavior, and it's shown here in this panel. So histograms here are the distribution of local abundances of molecular gas as a function of local density, and the solid lines are some existing analytical models. So all of them predict much higher abundances at this low metallicity. So Eva took the simulations and recalibrated a new model based on these results that captures this behavior. It's shown here with this magenta line, which describes the solution. So if you need a model for molecular gas to use in your simulations or analytical models or interpret observations at this low metallicities, this is reference to check. And also using the same simulations, we look at the variations of the local star formation efficiency or freefall time as a function of this varying metallicity and UV field. And again, there is a very weak dependence. So the values of efficiency are almost universal, and this is because of the efficient dispersal of this highly star forming regions with low level of turbulence, which results in this very narrow range of star formation efficiency is close to 1%, which can also explain why in the simulations of early galaxies, the star formation efficiencies are similar to what we observed in local universe. And I'll leave my conclusions and take questions. Thank you.
We have time for a quick question.
Just curious, you painted a picture where the Milky Way disk could start forming at redshift 7, and I'm wondering, I assume it was a fairly thick gas disk at that point. When do you find it transitioning to a thin disk?
We haven't, so the simulation was not run far. It was run so here show results to redshift 3. We ran to redshift 2, but they're like mergers that happen. So mergers is one of the ways to thicken the disk. And
so how thick is it?
We haven't compared like the thickness of the disk. What we compared is oh no, I'm not good with it. But yeah, so we haven't compared the thickness of the disk. So because yeah, the thickness can evolve.
Okay, so let's thank our speaker and all the speakers of this session. So we are a bit delayed, and we have 15 minutes for the break.